The immense velocity of an artificial Earth satellite directly determines the shape of its elliptical trajectory. Real spacecraft are always launched into orbits higher than 150 kilometers. The uneven equatorial bulge of the planet forces the satellite's orbital plane to undergo slow precession. The gradual atmospheric drag of the Earth inevitably leads to deceleration and total burnup of the vehicle.
Welcome. As your professor of physics for this explainer, we will embark on a detailed examination of the principles governing the motion of artificial celestial bodies. Our analysis begins on October 4th, 1957. Now, this date marks a fundamental shift, not just in human history, but in applied physics. The launch of Sputnik 1 was about fundamentally altering our interaction with the cosmos. So this singular event presented a profound physical question. How does an artificial object, subject to Earth's immense gravitational pull, manage to remain in the sky indefinitely? Well, the answer lies in a very precise, very delicate balance between velocity and gravity. So we'll proceed with a structured examination. We'll begin with the fundamental conditions for achieving orbit. From there, we'll build towards understanding how we describe them, the real-world forces that affect them, and finally, their practical applications. All right, let's move into our first section. Here, we're going to deconstruct the physics required to place an object into a stable path around the Earth. And as you'll see, it's all about achieving the right velocity. I want you to imagine an object launched horizontally from a great height, well above the atmosphere. Its path, its trajectory, is dictated entirely by the horizontal speed you give it at that moment of release. Okay, so what if the velocity is a little insufficient? If it's not quite fast enough, the object begins to fall back towards Earth. It enters an elliptical path, and that point where we launched it, that now becomes the apogee, the highest point of its new orbit. But at a very specific, critical velocity, something amazing happens. The curve of the object's fall perfectly matches the curvature of the Earth. It's constantly falling, yes, but the ground is constantly curving away from it at the exact same rate. The result? A stable, circular orbit. And this brilliantly illustrates the next point. What if we exceed that critical speed? If we give it even more velocity than is required for a circular orbit, it moves into a larger elliptical path. And now that launch point becomes its perigee, the orbit's lowest point. This critical speed, if we were to imagine launching an object right at the Earth's surface, ignoring the atmosphere, of course, is a fundamental physical constant. We call it the first cosmic velocity. Its value is approximately 7.91 kilometers per second. Just think about that. At that speed, an object would perpetually fall around our planet, constantly missing the ground because the Earth curves away beneath it. Okay, so we understand the basic principles, but how do we precisely describe these orbits in three-dimensional space? Well, what's really interesting is how we use a specific set of 6 parameters to do just that. These are known as the 6 orbital elements, or sometimes the Keplerian elements. And together, they unambiguously define everything about the orbit: its size, its shape, its orientation, and the satellite's exact position at any given time. So the first 2 elements define the orbit's geometry in its own plane. The semi-major axis, A, tells you the size of the orbit, and the eccentricity, E, tells you its shape. An E of 0 is a perfect circle, and as it approaches 1, the orbit becomes more and more stretched out. Now we need to orient that plane in 3D space. That's where inclination I comes in. It's simply the angle, the tilt, between the satellite's orbital plane and the Earth's equatorial plane. So an inclination of 0 degrees means it's orbiting right above the equator. The longitude of the ascending node specifies the rotational position of that tilted plane in space. It measures the angle from a fixed reference point in the heavens to the exact spot where the satellite crosses the equator while heading north. So now our orbital plane is fixed. But where within that plane is the ellipse oriented? That's the argument of perigee. It defines the orientation of the ellipse itself by measuring the angle from that ascending node to the perigee, the orbit's closest point to Earth. And finally, the last piece. To locate the satellite, we just need a starting point in time. That's the time of periapsis passage. It specifies the exact moment the satellite passed through its perigee. And with that, we have all 6 elements. Now this all sounds very clean, very perfect, But in the real world, these idealized Keplerian orbits don't last forever. They are constantly being disturbed by what we call perturbing forces. And for satellites in Earth orbit, the two most significant perturbations are the planet's own imperfect shape, the fact that it's not a perfect sphere, and the tiny amount of resistance from its upper atmosphere. So, this is crucial because the Earth bulges at the equator, there's extra mass there. This exerts a torque on the satellite's orbital plane. It doesn't cause the orbit to decay, but it does force the entire orbital plane to slowly pivot in space, a phenomenon known as precession. Atmospheric drag, on the other hand, is completely different. It's an energy-dissipating force. It acts like a brake, slowly chipping away at the satellite's energy, which reduces the orbit's size and inevitably leads to a final spiral and re-entry. You might be thinking this is all very academic, but this rigorous physical understanding, it is the absolute foundation of technologies that, frankly, define our modern civilization. Think about it, from global positioning and communications to climate monitoring and pure scientific discovery. None of it would be possible without this. Our mastery of orbital mechanics is truly indispensable. And so we conclude with a thought. As we look beyond Earth, towards a more permanent presence in the solar system, we must ask, what new perturbations, what new multi-body problems will we need to solve next? The principles we've discussed are just the beginning.
Thank you, friends. Strive for understanding and become wiser. See you soon.